This is the expression of charge density, and this is the expression of current density. I claim that this expression is of for current density. Since I am claiming that this expression is of for current density, I mean this is Minkowski for vector, then it should be invariant under Lorentz transformation. As you know, the definition of vector is a vector is a mathematical object that transforms between coordinate system in certain way. Here, R vector is of Minkowski space, so it should be transformed between two Minkowski space in according to Lorentz transformation law. And I mean the component of this for velocity, this for current density should be transformed in such a way that norms, if I take norms of this, then it should remains invariant. Uh, I mean, it should remain same between two different Minkowski frames. So, how can we prove this? If we see that these four expression, this is for velocity, this is for acceleration, this is for momentum, and this is for force, then we see that in this expression we have defined these as using invariant for vector invariant quantity. I mean, here this is for coordinates which is Lorentz invariant, and this is proper time which is invariant. So combination, so differentiation of these is also are also invariant. So due to this, this is for vector. And similarly, since this for velocity is for vector and this is a constant Lorentz constant, so this is also for vector for acceleration. And similarly, this here the small m is a rest mass which is in, it is not a relativistic mass. The small m is rest mass, although both are constant scalar number, but m is a Lorentz scalar, it will remain same if it is rest mass. The definition of a scalar is not that it should be, it should not have the direction. The definition of scalar in broader way is that it should remain invariant under coordinate transformation, and rest mass is that type of quantity. So combination of these two, which is for momentum, which is this and we can say this is or moment or for vector. And similarly, since this is Lorentz invariant and this is also Lorentz invariant, and differentiation does not change the fact that these are Lorentz invariant, so a combination of these are Lorentz invariant. So this is also for vector and it is known as for force. So if I can show that these all combination is a Lorentz invariant, then I can say that this is for vector and especially for current density. So, but as we see that we can say this is Lorentz invariant because this is for coordinates, but this time, although it is a scalar because time has no direction, but it is not Lorentz scalar. It will change under coordinate transformation. I mean, if we go from one coordinate to another coordinate, and this is also Lorentz. This is not a Lorentz invariant. This is direct delta function in 3 dimension because the argument, not because this is in 3 dimension, because the argument is Lorentz invariant, not Lorentz invariant. because it contains only three component of position, not fourth one, time component. And charge is Lorentz invariant. As the rest mass is Lorentz invariant, charge is also Lorentz invariant. So in this expression, this and this is Lorentz invariant, but this and this is not Lorentz invariant. But in few minutes I will show that the whole expression is Lorentz invariant, and this will, because this will happen because individually these are not Lorentz invariant, but the combination of these two, that is this divided by dt, is Lorentz invariant. So everything is the whole combination is Lorentz invariant. Due to this is Lorentz invariant. In showing this, I will use these two properties of delta function, which is if any function is multiplied by delta this type of delta function and integrated over, then the function will take the value which is not a dummy variable, I mean over which the integration is not being. And as we know that three-dimensional delta function can be written as the multiplication of three delta function in each direction. So I have written this expression again here, and since we know the relation between zeroth component of coordinates and time is that ct is equals to x naught, and I am saying that this I am placing here script n to for that. So it becomes it associates with each coordinates of each charge in Ford space. So I have, by this dt becomes this by the differentiation. So I have replaced this expression dt by this, so whole expression becomes this. I am treating this as a function of x naught, and so if I do this, then I found that this will become function of x naught. Here x naught, here it is, here the meaning of x naught is as follows. If you see that here vector x and here is vector s and vector x and vector x, and here vector x is denoting the position of each charge, and here the vector x is the position at where we are observing. Here charge density, current density, here current density is, and here charge density. So this is the time component or zeroth component of 4 coordinates where we are measuring the charge density. And here I also say that this is also equals to this, I mean Cp. So there is nothing changed in the expression, but if this argument is replaced by this, although there is logical error, because if I am claiming that this and this are equal, then this function, no, there is no logical error, I think. Yes. So after this, by knowing this fact, my current density will be equals to this, because of this logic, this fact, and with multiplication of this and integration of over all the time. zeroth component of time. So this and delta function and zeroth differential of for vector for coordinates. Now, if you see that I can combine these by using this factor and can return this as this here it is for coordinates and this also. So this becomes Lorentz invariant. This is Lorentz invariant because if any function of Lorentz invariant quantity is Lorentz invariant, I think it is, and this is Lorentz invariant. As I said, I can show I will refer various articles to some articles which claim that this is Lorentz invariant as the same as rest mass is. It does not change. It is same for all observers. So this is Lorentz invariant, and this is Lorentz invariant. Don't think this is Lorentz invariant. This is a component, one component or a component of four coordinates, and a component of vector is not invariant under coordinate transformation. The whole vector is a Lorentz invariant. Is invariant under coordinate transformation. So this is not Lorentz invariant. Here I have combined this and wrote this, and I wrote this as it is, but I use this fact again, and by this becomes c times dt. Numerator becomes c times dt, and the c and c times dt, the c of c times dt will cancel, and we get dt. And here I also replace dx naught n by c dt. So I get this. Now I will multiply numerator and denominator by gamma. Here I am saying that gamma is not a Lorentz invariant or Lorentz scalar because it will change from one coordinate to another coordinate. So we don't think that it is Lorentz invariant quantity. But I will combine this, and as you know, the combination of this is a proper time interval, and the combination, and I will also combine this with this, and this will become proper interval. Yeah. After combining this, the expression, the thing which is known as proper time is definitely Lorentz invariant. So C and combination of this Lorentz invariant and this and combination of this gamma and this gamma becomes d tau. So we see that this expression is equivalent to this, and the whole and this is equals to this. Here we see that each thing is a Lorentz vector or Lorentz invariant. C d tau q and this delta function, this coordinate, four coordinates, and this proper time. So the combination will be Lorentz invariant, or due to this is for vector in Minkowski's S. So we can say that this is for, if you are thinking our time, we can do this in the starting, that we can multiply numerator and denominator by delta gamma by gamma, and we combine numerator gamma of numerator with dt, so it will become d tau, and the gamma of denominator will keep here we as it is, and instead of this delta function we in the defining way we use for this delta function, then it will automatically feel that I am Lorentz invariant. No, it will not, because gamma is not Lorentz invariant. It will change because it in the expression of gamma, we as we know that there is velocity and velocity three component of, which is three component of velocity of, and it is not a Lorentz invariant. So we can't do this, and and yes, this encodes this expression encodes these two types of current density, because if we see carefully, then we find that the zeroth component, if we wish to see what is the zeroth component, then we find that the zeroth component will be the zeroth component of this coordinate differential, which is c d, which will be uh, c dt, and dt numerator, the dt which is in numerator and dt is in denominator, c dt, and the dt of numerator will be cancel out dt of denominator. So this expression, the zeroth component of this expression is this expression, and the exact thing is c. So zeroth component of for current density is charge density times c, and the remaining three component is is this, I mean, current density, three current density, because it will take three the special values. This coordinate differential will take a special value, and here is we have used a special value as PAPI here. So this is the, and we see if we see the norms, if you see the norm of this, then it will be Lorentz invariant, or it will not change for one one frame to another frame. So due to this is Lorentz invariant. So we can't think that we can write the expression of for current density, in which here we have used d tau proper time interval, and here we have used for delta function. And if in the starting, if we see that we have defined this for expression use in the defined way of these four expressions, we have used proper time, but here we have used only time y, because if we use the proper time, then this will not, then in this expression this quantity will not be Lorentz invariant. So due to this will not be, but the combination of this is, so this is my thing. I was saying that vector is not that it is invariant under transformation of coordinate system, or the vector is a mathematical object that transfer between coordinate system in certain way. Here, if you see that, you will find that it is not defined, it is not complete definition, but it is here the certain way is the way that we want. Here we want that it transform according to Lorentz transformation for vector.